Sometimes nucleophiles will attack atoms that don't at first seem like electrophiles. They don't seem like they have any positive charge on them. And that's because the only way that you would be able to recognize the electrophile is if you are able to recognize resonance and to imagine the resonance pattern that you get there. So for example, if you had a nucleophile, let's say you had some molecule with a full negative charge, where would that attack here? Now in the instructions they say each of the following compounds exhibits two electrophilic centers, and identify both. Maybe one that would be a little easier to see is this carbon right here. The carbon is double bonded to an oxygen. The oxygen is slightly negative, the carbon is slightly positive. So sure, if this nucleophile has a full negative charge, that's definitely one place it could attack. What may not be as clear, though, is that the nucleophile would also attack this carbon there. And at first blush, that makes no sense, because if anything, what's there is another nucleophile, the pi bond. But there is actually an electrophile there, and it's coming from resonance. So let me redraw this molecule. We have 2, 4, 6, 8, 9. 2, 4, 6, 8, 9. So here's our original molecule, this cockroach repellent that's found in cucumbers. And the first thing you'd want to notice is that we have a resonance pattern. We have a pi bond between two atoms of different electronegativity. So you draw the brackets to warn the world that you have resonance, and that the true structure is not going to be any of these structures within the brackets. It's only going to be the average of them. And you remember that when you have that pattern, the pi electrons go onto the more electronegative atom. That's what gives you the other resonance structure. So in this other resonance structure, we'll take that molecule, and we would have those electrons becoming a lone pair. So if in the first molecule there were 2 lone pairs, well now there will be 3. 2 of them are the electrons that were in the pi bond. That produces a negative charge on that oxygen, and it produces a positive charge on the carbon. Now notice that carbon, the carbocation there, that carbon with a positive charge, that positive charge is allylic to this lone pair. That's another resonance pattern. And so allylic to that pi bond. And so that pi bond would go towards the positive charge, and you'd get a third resonance structure. That would be with these pi electrons going toward the positive charge, and now the positive charge has moved over to that atom. Now none of these molecules represents the true structure. The true structure is the average of them all. But do you see that when you take the first, the second, and the third, and you average them, you end up getting a slight positive charge on that carbon. Now the only way you would see that is if you drew the resonance structures. And so you can see how important being able to visualize resonance quickly is going to be when you're trying to figure out where a nucleophile would attack. It's not just going to attack at the carbon that's double bonded to the oxygen, it will also attack on this other place that, if you don't know about resonance, you would never expect. But with resonance, you can see that position is an electrophile. So let's go through that thought process again. We want to identify the 2 nucleophiles in each of these molecules. The 2 electrophiles in each of these molecules. So Nootkatone is found in grapefruits. If a nucleophile were going to attack this molecule, where would it attack? Well, we definitely have a slightly positive carbon double bonded to the oxygen. So that's definitely one place. But notice that we have a pi bond between 2 atoms of different electronegativity here. And so we have resonance. Anytime you have resonance, you draw the brackets to warn people. The true structure is going to be none of these structures. It's going to be the average of them all. So I'll draw this molecule. Let me draw that a little better. Notice that we have some chiral centers here. So I'll draw this molecule, and we have that pi bond between atoms of different electronegativity. So if we want to get the next resonance structure, we take those electrons in the pi bond and we put them on the more electronegative atom. That gives us the next resonance structure. So we end up with this oxygen had 2 lone pairs to begin with. Now it will have 3 and a negative charge, and the carbon will have a positive charge. Notice that we now have a new resonance structure. The positive charge is allylic to this double bond. So the double bond moves towards it to give you the next resonance structure. And in that one, this goes toward the positive charge, stabilizes it, but now you have a positive charge here. And so when you average all of these up, you will end up with a slight positive charge on this carbon. It has 0 in this one, 0 charge in this one, but it has a full positive charge in that one. Average them up and you have a third of a positive charge. And so you end up with a slight positive charge there. So if you had some sort of a nucleophile and it were going to attack this molecule, it would attack it in 2 places. It would attack it in the place we saw first, the carbon double bonded to the oxygen, but it would also attack it here. And if you didn't know about resonance, you would never see the reason why. And you wouldn't be able to predict the correct product for that. So here we have our carbon. This is responsible for the smell of spearmint. We have a chiral center here, but importantly, we have, if you were to first try to look for the electrophilic centers, it would seem like you only have one. You have the slightly positive carbon that's double bonded to the really electronegative oxygen. But we have a resonance pattern. We have a pi bond between atoms of different electronegativity. And so to really visualize all of the possible electrophilic centers, we have to draw each of the resonance structures. So let's start just by drawing that molecule. It's when hundreds of thousands of these wriggle into your nose that you experience the smell of spearmint. So we have those pi bonds between atoms of different electronegativity. When you're trying to predict the other resonance structure for that, you take the pi electrons in the bond between atoms of different electronegativity, and you move them to the atom that's more electronegative. That gives you the next resonance structure. So here, that oxygen, which had 2 lone pairs, now has 3. It has a full negative charge, and the carbon it's bonded to has a full positive charge. That positive charge is allylic to this pi bond. So, when it's allylic, to get the next resonance structure, that pi bond moves toward the positive charge to help stabilize it. And so if you were to draw that last structure, you would get new pi bond here and the full positive charge on this carbon. So if you were to average all of these up, you'd see that 0 charge, and a full positive charge, you would have a third of a positive charge on this carbon there. So if a nucleophile were going to attack this molecule, where would it attack? Well, if you only predict that it would attack this carbon double bonded to the oxygen, you would only be half right, because also it will attack this carbon here, and the only reason why, the only way you'd ever see the reason why for that is by drawing the resonance structures. And you can see that when you draw the resonance structures, that carbon there has a slight positive charge in the true molecule. So watch out for resonance. In order to predict the right product, you sometimes have to think about how the electrophile changes when the resonance, when you draw these resonance.